Uh, Very good evening to this second Professor N.K. Bansal Memorial Lecture Series. We are starting dot at 5 o'clock as the class of Professor Bansal would have started dot at time. And we are remembering him because of his immense contribution in life of each student or each one who came in touch with him. And let me just still revise the contribution of Professor Bansal, although I need more than half hour or 1 hour for doing that, but just the highlights. So Professor Bansal, he taught for about 25, 30 years at IIT Delhi. Prior to IIT Delhi, he was teaching at Stephens College in Delhi, and he was working at Center for Energy and Center for Energy Studies, and he also worked as head of Center for Energy Studies. When Professor Vishal and myself we were studying there, he was there. He has supervised 38 PhD students. More than 300 research papers were authored by him. 17 books. Few of the books are widely referred internationally as well. Uh, he has he had completed 22 national and international projects, and he had close association with German universities, in addition to universities in US, Italy, and in Germany. He had about 10 different universities where very active collaboration was there. And just an example of that I saw in 1997 when I went to University of Essen under one of his projects. I was treated as a VIP just because of the fact that I was student of Professor Bansal, and I was representing him in that project in Germany. So that was the respect he used to get everywhere he was active. Uh, he also worked as vice chancellor of Sri Mata Vaishno Devi University, and in fact, he practically handcrafted that university because when he took charge, even the boundary wall of the university was not there. And then we witnessed all the beautiful buildings and the beautiful planning of the university happening and then getting implemented in his tenure. After his superannuation from IIT Delhi, he worked as syntax chair professor at CEPT University, and he continued to be advisor for a consortium of German universities in India for various collaborative activities. Professor Bansal was very actively associated with Ministry of New and Renewable Energy, Solar Energy Corporation of India, Department of Science and Technology, Planning Commission, CEA, SOCHAM, and many other important organizations, USAID, where our guest speaker today, he was working that time. He himself will tell what kind of association they had. I think Professor Bansal, our speaker, Mr. Padmanaban, they both were uh, architects of energy efficiency in buildings in the country, actually. So, building energy efficiency was the key area where Professor Bansal had immense contribution. But other than that, also he had a lot of important areas. And one very important thing that he had coming out of his research desk was climatic classification of India. So the 5-zone climatic classification in the country was also done by him under an Indo-German project. The Energy Conservation Building Code, the first version of it, 2007, he was chairing the committee of that along with other colleagues in the committee. A few of the things that everyone would have learned from him who worked with him, like us. One first one was punctuality, and he used to hate being late. He was never late. In the tenure of 25 years of my association with him, I never saw him coming late. In fact, he's used to say that if you are coming dot on time, you are actually late. Wherever you have to go 5 minutes before the time that was there. Uh, the field of energy efficiency in buildings through simulation is brought to India by Professor Bansal, other than Professor Bansal. So simulation, energy simulation, when mid 90s and late 90s, we used to talk about energy simulation that we learned from him. People used to say what you're talking about. They had never heard of those things that time. But now we can see that simulation is mainstream and people are using it extensively. We can see that Professor Bansal was father of building energy simulation in India. Uh, Window energy efficiency was one of his favorite fields, what Mr. Padmanaban would remember. So earlier people used to say what is great in Windows, but then he brought the knowledge of energy efficiency in Windows to India. And there are a lot of other contribution. So, as our tribute to his work and his contribution in technical knowledge, as well as shaping lives of each one of us who has worked with him in one or other, we are having this second Professor N.K. Bansal Memorial Lecture. I would request one of his favorite students, Professor Vishal Garg, to kindly introduce the speaker of the day, Padu Padmanaban. Dr. Vishal, please.
Thank you, Professor Mathur. It's a privilege for me to be introducing Mr. Padmanaban. So Mr. Padmanaban was the former program director of the South Asia Regional Initiative for Energy and senior energy advisor for USAID India's bilateral program. He had served with the World Bank, Washington, D.C. as an energy efficiency specialist and was a visiting fellow with the King Abdullah Petroleum Studies and Research Center, Riyadh, Saudi Africa. He has over 4 decades of experience in the design of national and regional energy efficiency programs, power sector reforms, regional energy integration, energy water nexus, clean energy, and energy access projects, including the planning and establishment of national and regional centers of excellence in energy efficiency. He is a founder member of CII Green Business Center, the Alliance for Energy Efficiency Economy, AEEE, India, and former trustee of Altec Foundation, a Bangalore-based NGO devoted to sustainable development. He was a member of Climate Investment Fund-sponsored international expert group tasked to select countries to accelerate coal transition, which was announced at the COP26 at Glasgow, UK. Mr. Padmanaban is author of a pioneering book titled First Fuel, India's Energy Efficiency Journey, which is published by Pan Macmillan in July 2021, that recounts the evolution of energy conservation and management in India since the early 70s and provides approaches to mainstream and capture the benefits of clean energy solutions in the country to mitigate greenhouse gas emissions and to address climate change. He is recipient of several international and national awards in energy management and efficiency. These include the Regional Energy Manager of the Year 2019 award by the United States Association of Energy Engineers, the World Clean Energy Award 2007 by the Swiss-based Transatlantic 21 in global recognition of his achievements in advancing energy efficiency and renewable energy. Recipient of Hall of Fame Award by the Indian Green Building Council in 2013, the All India Power Award in 2010, the Energy Professional Development Award 2008 by the Association of Energy Engineers India. Mr. Padmanaban taught at the School of Advanced International Studies, Johns Hopkins University, Washington, D.C. Over to you, sir. Thank you.
Just before Mr. Padmanaban starts, participants can type in their questions or queries in the chat box, and Mr. Padmanaban would address those questions after his talk.
Thank you. Should I share the screen now, or should I share it before I launch into my slides? I think I'll share it when I launch into my slides. So let me begin. First of all, sincere thanks to IBPSA, the International Building Performance Simulation Association, particularly Dr. Jyotirmay Mathur, the widely respected president of IBPSA-India, and Dr. Vishal Garg, for inviting me to deliver the Professor N.K. Bansal Memorial Lecture 2022. I attach a lot of value to the opportunity to honor Professor Bansal, a preeminent intellectual in the field of energy management, energy efficiency, and building energy performance. I had the privilege of meeting Professor Bansal in 1982, and thereon had a 4-decade-long association with him. I vividly recall my first meeting with him at IIT Delhi Center for Energy Studies. What prompted that meeting was a reference by an official from the Ministry of Industry who suggested that I meet up with him. At that time, I was working with the National Productivity Council of India, as a fuel efficiency engineer. The NPC had been tasked by the Ministry of Industry to prepare a document, a policy document on energy conservation in industry. And an interministerial working group had been established to guide the NPC in this document preparation. The interministerial working group directed us to have a small section in our report on energy efficiency in buildings. At that time, in the early 80s, there was very little information, knowledge, or understanding of energy use in buildings, and hence this official in the Ministry of Industry suggested that I meet with Dr. Bansal. I had this meeting with Dr. Bansal and several meetings after that, and in all the meetings I found him to be extremely hardworking, resourceful, productive, and above all, very helpful. But what really stood out was his curiosity. He was curious about energy efficiency, energy economics, energy planning, and as we all know very well, and as well mentioned by Dr. Mathur just now, he was one of India's prominent expert on passive building design. He advocated strongly, for instance, for using early design principles at the whole building level. He was probably the earliest, probably the first user of building energy simulation and modeling. And his focus extended to energy economics, cost efficiency, and to energy planning. And I understand that he introduced the Markle software to IIT faculty and students. The Central Electricity Authority those days used Markle as a means to optimize power sector planning, that is, looking at power sector through an integrated resource planning prism of integrating generation, transmission, and distribution. Clearly, Dr. Bansal had, and Dr. Mathur mentioned it very clearly, the unique ability to straddle the three disciplines of building energy design, energy economics, and energy planning. As mentioned by Dr. Mathur just now, he authored over 300 papers, mentored, I would imagine, at least 100 PhD and MTech students, wrote 17 books, and made other significant research contributions. The three key attributes of design optimization, economics, and planning are some of the common threads in his vast research work, including the power of critical observation and expression. I deliberated quite a bit inwardly on an appropriate topic to honor the memory of Professor Bansal. This extraordinary intellect that Professor Bansal represented. Also I was conscious that 2 months ago, in November last, was the COP26 meeting at Glasgow, UK, where the subjects of decarbonization and net zero loomed large. Given the Professor Bansal context, my thoughts started centering around energy efficiency, whether it was time for India to begin to reimagine energy efficiency and see it part of an overall strategy to advance goals for net zero and deep decarbonization. Putting the two elements of today's lecture together, first, Professor Bansal's exemplary commitment to energy efficiency and the need to reimagine it. And second, the meaning of net zero and how to get it right. I determined that the best way I can pay tribute to Dr. Bansal is to focus on a topic that threads both these elements. That explains my topic for today. First fuel, India's quest for decarbonization. The term first fuel, as we all know, stands for energy efficiency. My lecture for the next 30 minutes would have two segments. In the first segment, I'll briefly recount the evolution of energy efficiency and set that as a context to reimagine energy efficiency for the future. In the second segment, I'll discuss the meaning of net zero and how we as a nation can get it right to contribute to deep decarbonization. The first attempt at decarbonization was in the early 70s was in Mumbai. And at that time, the term decarbonization was not in the lexicon, neither was climate change, and certainly not net zero. It was in the early 70s in Mumbai, in the textile industry, where there was an arrangement to substitute high carbon coal by lower carbon fuel oil. It was by happenstance, it was mainly by accident. But yet that laid the foundation for energy efficiency in the country. I don't have time to describe the incident that propelled the country to move towards adopting energy efficiency. I've mentioned it in some detail in my book, First Fuel, India's Energy Efficiency Journey. But that actually signals the beginning of energy substitution, followed by fuel efficiency, followed by energy conservation, followed by energy efficiency over a 2.5 to 3 decade period, and today is being followed by energy productivity. There have been several studies which have indicated that if we were to pursue energy efficiency to its logical conclusion, half of our decarbonization target could be met. There are massive opportunities and potential in the industrial and in the building sector for saving energy, since both these sectors put together account for 70% of the total energy consumed in the country. The question to ask is, can we save an additional 20 to 30% energy without investing in newer technologies with existing equipment and existing processes? There are both tactical, strategic, and civic dimensions to this question. The short answer is we can, if we follow an integrative approach to energy efficiency. Before that, we need to understand the mapping of energy efficiency opportunities to achieve net zero, and through that achieve deep decarbonization. So let me show you the slides and we'll take it from there. So we can, are the slides visible properly?
Yeah.
Okay, that's the subject, First Fuel, India's quest for decarbonization. This slide is an attempt to map industrial and building decarbonization measures and technologies. There are 4 quadrants here, and the lower right-hand quadrant is what I call as the quick fixes. I don't have to spend much time on this. It's well known, their first aid measures, most of Indian industry follows them. The second quadrant is what is known as must-dos. And these are measures which involve investments in individual energy efficiency measures. The operative term here is individual technologies. They could be things like waste heat recovery or efficient motors or efficient boilers or efficient insulation and so on and so forth. But they operate individually without considering integrative designs that optimally combines these individual technologies. So when we look at individual technologies, we are achieving only a fraction of the energy efficiency potential available and perhaps even overstating its cost. The third quadrant is the quadrant which I'm going to discuss in some detail in the next few slides, and these are integrated designs. These are technologies such as pinch point process changes in chemical process industry, integrative designs of piping, pumping, lighting systems, both in buildings as well as in industry, HVAC systems, then advanced heat power cycles and so on. I'll come back to quadrant 3 in a moment. Please bear with me. And then you have quadrant 4, which are transformational technologies. These are technologies which are a little bit in the future. They involve circular economy, digital manufacture, nanotechnology, and so on and so forth. But coming back to quadrant 2, Indian industry is by and large in quadrant 2. Quadrant 1 is, of course, history. I mean, most industries have achieved most of the housekeeping measures. but they're in quadrant 2, knocking on the doors of quadrant 3. And that's important to understand because there are large potential savings, as I mentioned, in CapEx and OpEx if one were to follow integrative designs. Now, the question is, we need to understand what are the limitations of energy efficiency designs as of now in Indian industry. See, to understand the limitation of energy efficient design as they relate to individual technologies, our approach is typically stylized to develop efficiency technologies around individual standalone systems, as I mentioned, not on design methods that are inclusive. We do not typically look at upstream and downstream impact of an energy efficiency measure. So let's observe the limitations of energy efficiency design in this graph. The y-axis, the marginal cost of efficiency improvement, meaning the marginal cost for every additional or incremental energy savings. It's a steep curve, and hence the marginal cost of energy savings increases for every unit of incremental savings. On the x-axis, we have the cumulative energy savings. The law of diminishing returns applies here. In other words, the more efficiency we seek to obtain, the more steep is the marginal cost of the next increment of savings until it becomes too costly and we stop. In other words, we stop when the marginal cost of saving an additional unit of energy is greater than the unit value of the energy saved. We stop at a point where it does not make economic sense to tap any further energy savings because it's not cost effective. We do not want to cross the cost effective limit. So can we reimagine energy efficiency and save an additional 20 to 30% more energy at a lower marginal cost of incremental savings? The next slide shows how that can be done through integrative design, where the marginal cost of energy savings is lower if one captures the upstream and downstream benefits of energy efficiency, and hence 20 to 30% additional energy can be saved. Now, this is integrated design, and what we are doing is looking at the upstream and downstream impacts of energy efficiency measures. This enables one to tunnel through the cost effectiveness limit that I mentioned earlier. The barrier that held us back earlier, when we look at the prohibitive incremental cost of energy saving, is no longer a barrier if our approach is integrated. What does this mean? Let me give you a quick example of thermal insulation. We choose the minimum economic thickness of insulating wool that repays its marginal cost from the saved marginal heating energy. But this approach is focused entirely on the insulation technology and nothing else. It does not consider the potential impact of heat loss reduction on the size of the boiler, on the size of the burner, on the size of the ducts, on the size of the pipes. All of these equipment, the downstream equipment, can be reduced, and hence the capital cost can be lower. Furthermore, and I think this is the most important point, the marginal energy savings potential of these incremental, or rather these integrative redesign approaches would bring in 20 to 30% more savings in energy, both CapEx as well as OpEx, at a lower marginal cost of incremental energy savings. Let me give you a few specific examples. But before we come to the examples, I will very, very quickly look at the integrative energy efficiency design principles. I don't have the time to go through all of them. There are 12 basic principles. I'll just focus on 2 of them. One is the issue of defining the end use. See, there's a tendency, first of all, there's a tendency among designers and shop floor engineers to think that radical out-of-the-box thinking on energy efficiency is too costly. That's not necessarily so. these 12 measures will tell you that it can be even cheaper. But keeping that aside, and since time is off limit, I will just focus on two measures, end use, and the second one was upstream and downstream. On defining end use, there's a tendency for designers to focus on this object to be designed and not what it is used for, and for what purpose it is used for. I'll give you a very simple example of the drill and the hole. See, you need to drill a hole, and all the effort is on the choice of the drill bit, and very little attention, if at all, is on the hole, the size of the hole, the depth of the hole, the location of the hole. This happens time and time again in industry, where the end use purpose is ignored and the process is focused upon. The other point is on downstream and upstream impacts, the point that I made earlier. Saving energy downstream will have a compounding ripple effect on the upstream and vice versa. I can't do it any better than quote Dr. Amory Lovins, the chairman of the Rocky Mountain Institute. He gave this speech in Jaipur in 2017 at a conference organized by the Alliance for Energy Efficient Economy. And this is what he said. Energy end-use efficiency's potential is large and little tapped. Yet all official studies substantially understate its potential and overstate its cost because they focus on individual technologies, as I mentioned earlier, without considering integrative design that optimally combines those technologies. Integrative energy efficiency design principles optimizes the performance of industrial processes, machines, and buildings by collaborating in diverse teams to understand how the parts work together as a system, then turning those links into synergies. Let me now give you some examples of integrated design. Several examples of integrated energy design, just a few that came to mind. We'll obviously not have time to go through all of them, but the classic issue of big pumps, small pipes, and big pipes, small pumps, I'll elaborate a little further in a slide or two. Industrial process optimization, waste heat management, combined heat power generation, water energy nexus, lighting optimization, I'll try to give an example on that, chiller optimization, and so on and so forth. This is the question of small pipe, big pumps, or big pipes. See, it is well known that motors account for 60 to 70% of LCD use in industry for pumping, for liquid pumping, for operating compressors, blowers, fans, and so on and so forth. If one looks at pipes and pumps, there are two fundamental equations that govern fluid flow. One is the Darcy equation on water head losses, and the other is the Darcy-Weinbach equation on friction loss in pumps, friction losses in pipes. The Darcy equation basically states that head loss due to flow reduces as pipe diameter increases. The Darcy-Weinbach equation states that friction loss in a pipe falls as a fifth part of pipe diameter. Now put together, the equations tell you that as one increases the diameter of a pipe, the size of the motor, the pump, the auxiliaries reduce. So you increase pipe diameter, pumping equipment costs reduce. The only thing that increases is cost. The only thing that increases in cost really is that of the pipe. That increases in proportion to the square of the diameter or the cross-sectional area. So pumping equipment cost reduces by a fifth part of the diameter. Pipe cost increases by only second part of the diameter. So when you look at the pipe as a component, which one does in a conventional design, the size of the pipe is limited by the cost effectiveness limit. You look at the incremental cost of the pipe and compare it with the incremental reduction in head losses and hence the energy savings. You omit the capex savings potential of the pumping equipment. An integrative design optimizes the whole system, yielding bigger pipes, smaller pumps, smaller capex, and smaller OPEX. Change in design mentality is required. Big pipes, smaller pumps, a corollary, design pipeline first, and then the pumps. So another very simple example, is very simple, that illustrates the basic principles of integrative energy efficiency designs. See, we spend a lot of effort and money on choosing a light lamp with the highest lumen efficacy, such as an LED, which has an efficacy of, let's say, around 120 lumens per watt, as compared to an incandescent, which has an efficacy of about 25 lumens per watt. But we ignore the task or application efficacy of the lighting system. We miss an important question. Is the light illuminating the table? Is the light illuminating the table? Or is it illuminating the whole room? Or is it illuminating the task that we wish to light up? As simple as that. So going in for high efficiency lamp and then ignoring task efficiency, they're not having an integrated design task lighting system. That's the principle and basic point. Let me change gears here and turn to another aspect, moving from integrative design to some strategic design principles. Design principles of energy efficiency, which will help us to reimagine energy efficiency. If you think for a moment, when we talk about energy efficiency, we always ask the question, how is energy used? That's the first question a building owner would ask, the first question an industrialist will ask, how is the energy used? And the answer is pretty straightforward. You do an energy audit, you identify the energy conservation measures, you prioritize the measures, and you implement those measures that make the most economic sense. End of story. Now, if you were to ask the question, what is the energy used for? Then the answer is very interesting. You will embrace a new concept, the concept of energy productivity, that is based on the principle of maximizing the economic value of energy. The energy productivity of a nation is the inverse of energy intensity, and it is the GNP divided by the total energy consumed. Energy productivity of an industry, of a company, is the total revenues of the company divided by the amount of energy consumed in a particular year. So energy productivity puts energy at the center of economic planning. It's a new policy narrative that is broader than energy efficiency. Why is that so? Now, if you look at aluminum ingots, do we just manufacture aluminum ingots, or do we go all the way and manufacture aluminum fuselages which can be used in aeroplanes? Do we manufacture cardboard, or do we go all the way and manufacture specialized paper? Do we manufacture just mild steel, or do we go all the way and manufacture precision alloy steels which can be used in precision machine tools? So many examples of this kind where you add value to the energy that is consumed. Recognize that the energy consumed manufacturing these value-added products is not much greater than the energy consumed in manufacturing the primary product. So with a little extra energy, you add much more amount of value, and value is what is important. Now, there are several comparisons between efficiency and energy productivity this table has, and I don't have the time to go through all of them, but the issue of individual technologies on energy efficiency, a point I made earlier, as against technological complementarity, is what you look for when you look for energy productivity. Energy efficiency is what I would call as a boiler room subject. It involves technical approaches towards saving energy. So that's why I call it a boiler room subject. Energy productivity, on the other hand, is a boardroom subject. It involves issues such as modernization, diversification, value addition, and so on and so forth. So it's a question that the boardroom is engaged in. The challenge in India, as we look at decarbonization, is how can we move energy efficiency from the boiler room to the boardroom? That's where the challenge lies. Because in energy productivity, you focus on the value that energy brings about, and the higher the value, the less would be the energy that would be required in order to meet a certain economic growth rate. Now, this point I'd already made, so I'm not going to cover it again. Do we maintain competitiveness of the economy through energy efficiency, or do we open up our competitiveness more globally by developing downstream industries, which are higher value added industries, such as aluminum and steel and fertilizers and so on and so forth. But I think the point is that we need to look at value addition. And that value addition can only be looked at if we ask the simple question, what is the energy used for? This is the graph of energy productivity in India and how does it compare globally between the years 1990 to 2015. Now, interestingly, in 1990 was where we had the economic reforms in India. De-licensing took place. Industries were able to go into higher capacities. They were able to modernize. And definitely there was an impact in the improvement in energy efficiency, in energy productivity. Energy productivity, that is the amount of energy used per unit GDP, or rather, the GDP growth rate per unit energy had to definitely improve by almost 72%. In the same period, all other countries did well. Germany increased by 22%, Australia 48%, USA 61%. Recognize that these were the G5 countries which were already operating at a higher level of energy productivity. But China, which had the same level of energy productivity as we had around 1985-90, actually improved a lot greater by 203%. Hidden behind these numbers is another issue, which has an impact on our decarbonization strategy. Hidden behind these numbers is the link or the coupling of energy and GDP. Now, in the G5 countries, Germany or USA, the coupling is absolute. Rather, the decoupling is absolute. So every unit of GDP increase, there's a reduction in the consumption of energy. So you don't have both of them moving lockstep in direction, but while one is increasing, the other is reducing, and it's an absolute reduction. In India, the coupling is also happening, the decoupling is also happening, but it's relative. What it means is that as we increase GDP, our energy consumption increases per unit GDP, but our rate of increase of energy consumption is reduced. So we have what is known as relative decoupling, whereas the G5 countries or G8, G7 countries have what I call as absolute decoupling. Now, if we have to move towards decarbonization and net zero, we need to move from relative decoupling to absolute decoupling. And that's very important. So that means the importance of energy productivity as part of our strategy to reimagine energy efficiency in order to meet our targets of decarbonization and net zero becomes extremely important. This comes to my last slide, where I would like to pull what I said, pull it together and relate it to net zero and decarbonization and how to get it right. We all know that decarbonization is the reduction of carbon dioxide emissions with the use of low or zero carbon energy sources, and be it gas, be it hydrogen, be it renewables, and substitution of coal and transiting away from coal. For instance, in our power sector, are steps required in order to meet our decarbonization goals. So, but decarbonization of a country's economy can lead to carbon neutrality or net zero. And it's very important that we understand that net zero refers to the balance between the amount of greenhouse gas emissions reduced and the amount from the atmosphere taken away through carbon sinks. So net zero or carbon neutrality is achieved when the amount added is no more than the amount taken away. It sounds simple, but it's a little more complicated than that. India has declared that it will have a policy of total net zero by 2070. And that's interesting, and I just want to deviate a little bit. It was in 1970, about 40 years back, that we began willy-nilly by accident moving away from coal to oil. Maybe the requirements those days required that kind of energy substitution. But through that process, a little bit of decarbonization of the economy path would have taken place, although that was not at all the intent of the government. Exactly 100 years later, we plan to decarbonize the entire economy. That is in 2070. So I just thought I'd mention that kind of coincidence. Now the question is, if you have to decarbonize by 2070 and achieve net zero, and I defined net zero just now, how do we get it right? That's the question. First of all, we need to appreciate that climate policy today has a new focus. That's net zero emissions. Now, some of you might recall that earlier climate policy, particularly under the UNFCCC studies of, I think that was in 1992, and then the Kyoto Protocol of 1997, they expressed climate change differently. At that time, it was expressed in terms of reduction in atmospheric concentration of carbon dioxide. And there was this discussion during those times of reducing carbon concentration or maintaining carbon dioxide concentration around 400 ppm. Today, that's past history. Today, we are expressing climate change differently as reductions, not in carbon concentration of CO2, but reductions through a specific target date for reaching net zero emissions. And that was first announced during the Paris discussions in 2016, and then reinforced in 2021 at the Glasgow COP26. So this is the point. The objective is to keep the average temperature rise to 1.5 degrees centigrade. That's the objective. Net zero is to 100 to 1.5 degrees centigrade is a choice by society, and this choice has been based on scientific evidence that existential threat to mankind would happen if the temperatures were to go to 2 or 3 degrees centigrade. If it goes to 2 degrees centigrade, we'll have irreversibility, which we will not be able to deal with in terms of changes in our climate, changes in the oceans and tidal waves and rise of the sea and so on and so forth. And if it goes to 3 degrees centigrade, all bets are off. So in their collective wisdom, they took a decision that we will keep temperature rise to within 1.5 degrees centigrade. So the objective is to keep the temperature rise within 1.5 degrees centigrade. Physics implies that there's a finite budget of carbon dioxide that can be allowed into the atmosphere to keep acceptable rise to 1.5 degrees centigrade. And acceptable rise is a societal choice. So net zero is more than a scientific concept, although I defined it as a scientific concept. But when you tie it up with temperature rise, you'll find that net zero is also has a societal implication. It has a political implication. It has an economic implication. I think that's very important. There are ethical issues. There are just transition issues. We go on on the issue of just transition, changing over from coal to renewables in this country in the power sector will open up a Pandora's box of ethical issues, of just transition issues, socio-economic issues. And then there are varied political and economic issues. Now, getting net zero, the frame of reference, right, is essential. That, I think, is the point I'm trying to make. Getting it right and the frame of reference, given that net zero operationalizes in various spheres, not just in the technological sphere, but also in the political and economic sphere. Let me stop here with a brief remark. Vigilance, I think, is the only thing that will ensure us to get net zero and decarbonization right. I think the principles that Professor Bansal stood for, based on careful observation, simulation, analysis, computation, and transparent commentary, will hold us in good stead in ensuring that we get net zero right. Once again, I would like to thank you for your patient listening. Thank you.
Thank you very much, Mr. Padmanaban, for covering this topic from the integrated design to the decarbonization. Recently had discussions in COP26. We have some questions in the chat box, so I will take up the first one coming from Arun Bhandari. He has written that integrative design is a great strategy to push for energy efficiency due to advancement in energy technologies in the information science. What are the challenges to carry forward the concept of integrative design? How the integrative design will be used by the new generation of engineers?
Excellent question. See, it's not as though integrative design is not totally followed. By and large, process industry, refineries, chemical process industry, fertilizers, petrochemicals, they do follow integrative design because that's the nature of the process. Cogeneration is an example of integrated design where you integrate heat and power. Water energy nexus is another example of integrated design. The challenge lies when we look at the small and medium scale industry, where they look at energy efficiency as an individual technology. And that's where I think the challenge is. And there are software tools which we need to kind of now adopt so that they can look at the upstream and downstream impacts of energy efficiency measure that they incorporate. Remember, integrative energy design does not explore additional efficiency measures. They look at the measure that you have already incorporated and look at how that measure could have an impact on the size of your pump or your size of your boiler or your size of your system. There have been cases in the past where efficiency measures have resulted in equipment operating at suboptimal capacities because you had designed the equipment much before you had even designed the measure. There was this question of pipes, big pipes, small pumps, or small pump, big pipes. Perfect example. Many a time, even in buildings, we go down to the ground floor of the building or the basement, you will find that the pumps and the pipe size don't correlate. And even the pipes also are rather winding and so on and so forth. The head losses are very high. Until and unless you do the piping first and then you go in for your pumps, rather than going for your pumps first and then going for the piping. So it's a question of the approach more than anything else. And I think the technology issues, the design issues are fairly well known. It's just a question of prioritization of that.
Thank you. There is another question which is coming from Professor Tarush Chandra, and he's saying, seeing that decoupling in India is different from G7 countries, what should be the way forward in favor of India?
Can you repeat that? I lost you, Professor Mathur. Can you repeat that?
Seeing that the decoupling in India is different from the other countries, especially G7, what should be the way forward in favor of India?
Well, you're right. The decoupling in India, as I said, is relative. The decoupling in the G7 countries is absolute. And the way forward is to push for energy productivity in a much larger way than what we have done so far. See, energy productivity is the inverse of energy intensity. And reduction of energy intensity through value-added manufacture is probably the way forward. That is, in every sector of industry, we need to see whether the product manufactured has the value in the marketplace and whether we should manufacture those products rather than manufacture basic products. Now, to some extent, that is already being done. The market itself guides you to do that. People don't make just ingots; they make fuselages. They don't make just aluminum frames. They make aluminum fixtures and aluminum products, which are far more usable in the marketplace. And there are many examples in the other sectors too. But the question is, if we can go through our economic planning process and look at the role that energy plays and see whether energy is contributing to the value addition rather than energy contributing to the basic material manufacture, then I think that is one way forward. So it's re-examination of every aspect of manufacture, every aspect of value addition, and then going in for a program for diversification, a program for restructure. Now, the program for that, there was this case of a paper mill in eastern India, which manufactured cardboard. And they realized that they could actually use the same digester with some changes, of course, with different pulping technology, and manufacture specialized tissue paper. So with some additional capital investment, they made the change, but the value addition was so high that for the same amount of energy that they used to make cardboard paper, they ended up getting a far better return when they made tissue paper. So that's one example. And there are examples in every sector of industry. Now, can we do this at scale, replicate it? That's the point.
We also have among the panelists, Professor T.C. Kandpal sir. Sir also taught us when studying at IIT Delhi together with Professor Bansal, and he had a long association with him. So, sir, would you like to ask something to our speaker, Mr. Padmanaban?
Yeah.
And also we would request you to speak.
Yeah, thank you, Jyotirma. Thank you so much. It is really a pleasure to be here. I just got an opportunity to be here. I wish more of our students were here listening to Mr. Padmanaban, particularly the idea of integrating, the different possible measures. So it's really excellent. But I had one of the things you already answered while answering things. I was wondering that why emphasize on energy productivity? Why not speak in terms of energy intensity itself, right? Because energy intensity is, particularly students with scientific bent of mind perhaps would be much closer to this. That is one. Second one is that this, when you say decarbonization, are we talking of total decarbonization or net zero emissions? Because the two will have different implications. Because if you have more carbon sinks, in terms of forest or in terms of other mechanisms, perhaps net zero would have different meaning compared to total decarbonization. Just your inputs, please. Thank you.
I think on the first question, energy intensity is the inverse of energy productivity.
Sure.
And you're right. When we talk to engineers, they probably appreciate energy intensity, the amount of energy required to make a ton of, let's say, paper or a ton of sugar or whatever. It's where energy is in the numerator, the amount of energy, and the product manufactured is the denominator. So it's just a question of an inverse. But energy intensity takes you thus far in terms of understanding where the potential lies in advancing efficiency. Energy productivity takes you the next step further, at least the concept of energy productivity, of value addition. What is the next kind of product you can manufacture? So the importance is now changing from how energy is used to what is the energy used for. And energy intensity probably explores further how energy is used, whereas energy productivity explores what is the energy used for. And I think it was a more forward-looking kind of an approach. Now, for instance, the Chinese, for the reasons that you mentioned, Dr. Kanpal very rightly said, we are not going to focus on energy productivity as a strategic policy direction. We are quite happy with energy intensity because the economy decision making on modernization and all that is not left to the boards, it's left to Beijing.
Sure.
So they didn't have to worry. The companies had to reduce energy intensity. That's it.
Sure.
Whereas in free market economies, mixed economies like ours, where the boards take the decision in many cases on what product to manufacture and so on and so forth, the term energy productivity will open new vistas in their mind. Mm-hmm. So that's why I focused on energy productivity rather than energy efficiency. The second point on decarbonization and net zero. See, as I said, a very simple way of looking at net zero is how much of carbon you put into the atmosphere, how much of carbon you're abstracting from the atmosphere, and if there is a balance, then you have reached carbon neutrality. Now, decarbonization has another implication, which might go beyond the definition of net zero. That's the point you're pretending to make. When you go into renewables, when you look at hydrogen economy and renewable technologies and so on and so forth, which have little or no carbon at all, then getting them into the energy mix brings up a range of other issues. I think my point here would be that let's not quibble over definitions. Net zero as a concept is a scientific concept. The point I tried to make here was it is beyond a scientific concept. It is a scientific concept in terms of doing the energy balances. But since it's tied to temperature rise, and temperature rise is a societal concern, based on which we have agreed on 1.5 degrees. We could have well agreed on 5 degrees centigrade, just taking an extreme view. But common sense, good sense, scientific evidence says 1.5 degrees. Since we agreed on 1.5 degrees, we immediately know how much of carbon can be put into the atmosphere because there is a budget in the atmosphere, how much carbon each country can put into the atmosphere, and we have a good understanding of that. That amount of carbon you can put in the atmosphere is not a scientific concept. That is a social, technical, ethical concept. So net zero is a social, technical, ethical concept. If you look at it from that point of view,
sure,
then you recognize what it takes for us to meet net zero in 2070. Now, 2070 is about 50 years from today. Yes, we can probably achieve it. But I'm afraid we are not talking enough yet, maybe we will, yet, on these other dimensions of net zero. We are still looking at it as a scientific concept and moving forward. We ought to be looking at it from this broader vision. And institutions like the IITs are in a good position to do it because they have different disciplines. But these disciplines need to interact. The social sciences need to interact with the management sciences, need to interact with the technological sciences. And when all of them come together, then we will get it right. That's the limited point I wanted to make.
Thank you. Thank you so much.
So you've already answered the questions that has come further in the chat box, which says that do we have the institution and research capacity to achieve net zero by 2070? And what can be done to improve it? Maybe after listening to you, and I would like to capitalize upon the presence of Professor Kanpal on this. Sir, would you like to add something on especially this capacity, research capacity?
The answer would be yes. But as Mr. Padmanaban hinted, that perhaps a conscious focus has to be given to, looking at things holistically. I mean, it's not only technology. He mentioned I'm sure our audience must have heard him talked of just transition or the ethical issues of it. Or he gave a very nice example of having, transition from coal to renewables, so the kind of implications it would have for they all stakeholders with the coal sector, including, common people. So yeah, that's true. But yes, I can assure you that India per se definitely has the capacity to take the target of zero transition head on. Only thing is we have to really focus, all of us have to pull in our heads and capabilities together in that direction.
Absolutely.
Thank you.
I will say amen to whatever Dr. Kantpal said. We have the capacity, we have the capability. There are examples. Transition from coal to renewables in the power sector is a perfect case where we need to go for decarbonization, we need to go for decommissioning, but there are socio-economic issues. We have to ensure that the socio-economic conditions of the affected communities is not worsened or not affected. That's a challenge in and by itself. It's not a technical challenge, it's more of a socio-economic challenge.
And one last question, or rather, it's a comment from Mr. Adil, who's an independent consultant operating from Delhi. He has written that why can't we make simulation compulsory, because the pipe and pump problem that you highlighted and other things, they can be identified if simulation is done prior to such projects. So it's an extremely good suggestion, and
It's a good suggestion.
extreme simulation in
I think it
common
can be
life
done.
that would solve many of the problems.
I did not say anything which was rocket science. We go back to basic engineering, but it can be done and should be done. So, an energy efficiency strategy, for instance, in an industry, if it looks at downstream and upstream approaches, then software tools such as simulation tools would definitely apply. But it will depend on what particular application you're looking at. But it certainly can be done.
So it's an interesting discussion that is going on, and thank you very much, Mr. Padmanaban, for triggering our minds and showing us what are the issues and what are the possible ways. The discussion on the basis of the questions at the end was also quite interesting, and I am sure all of us would have picked up some or other research area, potential research area out of the discussion that we had. And that is exactly what seen him doing this at all the forums. He would pick most interesting and most important and then start working on it. And that is what we can pick up from the practices that he had followed during his entire research life and teaching life, and shared with all of us. So
that will be the best tribute. That will be the best tribute to.
Yeah. So with this, we come to the end of this second Professor N.K. Bansal Memorial Lecture Series. I thank first of all, I thank Mr. Padmanaban for agreeing to be the guest speaker today. Thank you, all the participants. Thank you, all the participants, especially who had shared their queries and made this interaction interesting. Special thanks to Kantpal sir for being with us in the panel and furthering the discussion with Mr. Padmanaban. Once again, thank you very much, one and all. We hereby close this. Thank you. Have a nice day.
Thank you.
Thank you. Thank you so much.
Vishal. Thank you, Jyotimay. Thank you, Dr. Kantpal. Thank you.
Thank you. Thank you, Professor.
Thank you, everyone. Bye.